Right, just to recap what we've been talking about, let's say practical issues with PID. So what you observe at the first part is quantization. And quantization is specifically a problem with digital devices. You don't see quantization error with analog devices, like the physical control valve controller that I showed you yesterday. That device would not suffer from this problem. You wouldn't get those little furry spikes. You would get something more like the right-hand side image. And the second is this idea that I have to realize the derivative. And so, as you can imagine, if I look at the ideal derivative term, that says tau d times dE dt, right? That's the ideal, that's the mathematical ideal version. But I can't actually build that device, and if I'm trying to approximate that device digitally, I would end up with something like tau d, and I would use a finite difference. In other words, if I look at the derivative, technically the mathematical derivative is a tangent, right, at a particular point. But if I'm sampling at points, I can just approximate that derivative by taking the change over the change, right? So I can say E n minus E n minus 1 over delta t. And that'll give me what is known as a first order finite difference approximation of the derivative. And that's what's happening in the TC Lab implementation. Now, this interacts in a specific way with the quantization error, because you can imagine that unless the noise is very large, each one, I will never see anything else than either a zero derivative. So if I zoom in on one of these little furry bits, right? If I zoom in on that, and I zoom in on time as well, I'll have a certain value as my baseline. I'll have another value as the next value up, and another value as the next value down. And what I'm actually seeing, what I'm sampling is, at this time I'm measuring this, and each one of those little furry spikes is another measurement which is just the next value available up, and then another measurement which is the next value down. So all of the parts that look like it's just staying at one level is actually like this. Right, so I'm sampling at those moments in time. So my derivative is only one of three values, given that it's like spiking up like that. It's either 0, or it is just the quantization, or the next amount up divided by the time, or it's the next amount down divided by the time. So it's always kind of just one of those values. And that's the only derivatives that I can calculate. So what that means is I'm not calculating the accurate derivative. I couldn't do that anyway, but I'm also being kind of stopped from doing that by the fact that I'm doing it in a discrete system like this. So that's the first thing. Just when you're trying to interpret what you're seeing, that's the first thing that you should think about is, because of quantization error and because of this finite difference, I'm seeing moves on my manipulated variable that is exactly just one of those values. And so even though my temperature is quantized, but my Q is actually not quantized, well, the available Q that I asked for is not quantized, I'll still see just exactly the same. I'll see that fur on my Q just like I see that fur on my T. So that's the first kind of practical problem that you see, and that explains at least why I'm not seeing like smoother curves, at least. The second problem is, you can imagine that if I have integral action, if I had a set point which was not exactly on one of those quantization values, that means I would get a persistent and remaining error. Which means that I would keep integrating that small error, and at some point that integral would get large, and at some point that would push my manipulated variable away from, let's say, whatever that steady state value was, until I drop through to the next quantization. And so what you will notice is if you run this for a very long time on the real TC lab or on the model, unless you chose a set point that is exactly on one of the quantization points, you will see this kind of slow oscillation. So you'll see if you run it very long, the error integral will very slowly climb or decrease because we are not exactly on set point. At some point, it'll get large enough that it'll push the temperature down or up. At that point, it'll like change the sign of the error, and I'll start eating into that error integral again. I'll either start increasing it or decreasing it. And so with this quantization error, you will find that even over very long times, you will see a slow movement. Now, you won't really see much in the temperature, but you'll see the error integral do this kind of slow up and down. It won't actually settle out to a steady value. Now, this whole observation, everything that I'm talking about now, is impossible to observe using the math that we're going to do in Chapter 10. Why? Because this has everything to do, this is just a practical issue that has to do with the fact that we are using a quantized measurement. Does that make sense to everybody? I hope that answers anybody's questions about like why they saw that slow oscillation of Q in long-run versions of this experiment. You can check that this actually works this way. So understand that there are issues of practical implications when implementing a PID, which, again, we won't actually see. Just like yesterday, I spoke about how incredibly positive the analysis will make a derivative look if we do the math just in the Laplace domain, because we're actually doing a lot better than we can in practice. A part of what I would like you to think about when we're doing the project for project part 1 is actually pulling out these practical differences between what we think we're implementing, what we would imagine if we just did the math completely on the model and completely in the Laplace domain, versus the actual thing that when we actually build it and we actually talk to an actual TC lab, how does that differ from this idealized, model? Okay, so the last thing I want to say while we're still on Chapter 7, and this is, again, when you read through the formulation of the project in the study manual, I've had a couple of questions about the project. The project description, the stuff that I expect from you is pretty much exactly as it is in the project description right now, so there's not that much mystery. I will be adding, as I mentioned, I'll be adding a little bit of a task of comparing results from previous groups. So right now, I wouldn't invest too much in actually writing a lot of code for the project right now. I think everybody's still getting the hang of everything. I'll probably be releasing those previous projects over this weekend. So if I were you, I would just be working on kind of getting a handle on how the stuff works and not really be writing a lot of code, because you're going to be critiquing a different group's project. So that's a whole thing in itself. But when you think about implementation, and especially when we're talking about simulating things on a computer, we have this problem that computers are discrete devices. And so, just like last year, we had a lot of trouble, I think, everybody understanding discrete simulation, because all the simulation we had done already looked like discrete simulation, right? I think I want to try and capture this idea of the difference between simulating a continuous device and simulating a discrete device. So recall that we've got this equation. So let's say I've got a PID controller. Let's keep things simple and just say I'm trying to simulate the action of a continuous PI controller. And so in the time domain, that means I've got this equation. If I was simulating that, if I were building a computer program that would simulate that, in the computer program, I would be forced to approximate that integral by a sum. Right? But the underlying assumption is, and so I would write code which would look something like so I would write that, and I would have something like so that would be my kind of approximation of an integral. And I want to be very clear that if I have this kind of code, conceptually, if I'm doing this for a continuous system, I'm interpreting this as a solution to a set of differential equations. So I'm saying I'm approximating this as the solution to a set of differential equations. So I'm taking my error and I'm multiplying that by dt, and this effectively is an Euler integration. An Euler integration. Okay, and I want you to understand that that sum there, conceptually it doesn't have to be that sum. I could use something like a third order Runge-Kutta or whatever, right? Like if I were just trying to solve this equation, I could integrate that set of differential equations using, good old ODE int or IVP, solve IVP, or any of these kind of higher order kind of methods. The method of calculating that integral is not integral to the operation of the algorithm. What is important is that I am calculating an approximate value for that integral. When you look at the way that we approximate now, or when we discretize and find a digital PID, so this is an analog. So I've got my analog PI controller, and I'm simulating that with a small step size so that I can get a good approximation of what it would actually look like if I would build that device using analog equipment. And if that device was talking to a real plant using analog everything. So what we're pretending in our head here is that there are no digital components here. The reason it looks like a step has everything to do with the integration algorithm and nothing to do with how the PI controller works. I want you to fix that idea clearly in your mind. Then I want you to understand that a digital PID controller, or a digital PI controller, for that controller, I would write code, and this is where it's confusing, is the code looks exactly identical. So if I were implementing now you can see I'm going to use the version of the algorithm that is in equation 7-26. And I'm just going to kind of write it out as Python code. So I'm doing exactly the same now. Now, can you see why I'm saying it's quite hard to understand why those are not, why is that not 100% exactly the same thing? So if you look at the substitution there, notice that I'm, in this form, I'm multiplying by dt over there, and in the form in the textbook, I'm calculating this running sum of the error, and then just like when I actually do the calculation, I'm multiplying by delta t over there. But as everybody see that when you compare those lines of code, they are the same code. They are doing the same calculations. So why is this confusing? It's confusing because it looks like it's doing the same thing, but conceptually it is doing very different things. Conceptually, the top equations are attempting to solve continuous differential equations. And conceptually, the bottom code is simulating a discrete device. The big difference will be from a practical point of view, if you are actually doing this, is that I would expect you to use very, very small step sizes for the top code, where you are trying to get very close to the solution of a continuous PI controller. And I would expect you to use the largest time steps that you can in the bottom code when you are simulating the action of an actual discrete controller. Because discrete controllers do not exist, or they don't actually execute at the times in between the times. And so we'll run into this. When I say conceptual difficulty, this is difficult in concept because it looks different. It is only, or it looks the same, it is only different in concept. And I think a lot of people aren't really clear on this distinction even now between discrete systems and continuous systems, because we cannot simulate, well, we can't actually have continuous systems on our computer. Right? And so it's a hard thing, because I'm saying, oh, no, here in the top code, here we're pretending everything is continuous. Do you see? Do you see how different that is from here? And everybody's saying, no, we don't see. We don't see at all, because it's exactly the same code. How can you be saying it's different if it's the same code? Well, it is the same code, but we're using it differently. Where it becomes different is if we're trying to simulate, and like, you know, it's weird, because the bottom code, a digital PI controller acting on a real continuous system. This is what you get when you have your PI controller simulated in code interacting with your analog TC lab unit. Okay, so if you think about how we will be doing control, we'll be doing control in exactly two ways in this subject. We'll be simulating exactly two cases. We'll be simulating a digital controller, right, running on your computer, interacting with your TC lab, or well, let's say, And so in every meaningful way, this is true. You have a digital control algorithm. If you are running that PID simulator, you have a digital control algorithm, and it is writing outputs to a real analog system. Right? Your TC lab exists in the world. It's not a weird simulation of a system, it's an actual system. It is right there. If you touch it, you can feel the heat at any given time. You will then measure that, and you'll actually be measuring sampled versions of that, and you'll be interacting in this way. So in terms of when everything is connected, when you have your USB connected and you've got your TC lab running, the TC lab is the only analog part of that whole system, right? The TC lab itself, the actual heaters and the actual temperatures and so on. Everything else, we're sampling, we're doing our control calculations in the computer, and we have a digital controller acting on the analog system. And weirdly, that is now the easy version of this, because we have the analog coming from the fact that you have a real analog system. So this is kind of why I want you to have the TC lab, so that you have a real system to work on. The second thing, and what we'll spend probably 80% of the time in this subject analyzing and simulating, is this thing that we actually do not have the ability to do in actual real life, which is that we will have an analog controller interacting with the analog system. And in that control loop, there is no sampling. All of the signals are continuous. Unfortunately, there's no way for us to gain access, no practical way for us to gain access to such a system. Does this make sense? So the analog controller here would be something which is like an ideal PID, or something which is like a real PID built out of circuits. And much of what we'll be doing in the subject is we will be simulating that analog system. And this is why this whole thing is very important. So we'll be taking this approach, the top approach, when interacting or when simulating all of the stuff that we're going to be doing in Chapter 10. Right? Because we're going to be saying, let's imagine we have a real analog system, which is not that hard to imagine, but then we'll also be saying, let's imagine we have an analog controller. When you put all of those parts together, you end up with a set of differential equations. In other words, there are no difference equations. You can take the Laplace transform of those equations, and you can analyze that system completely continuously. However, there's no direct way of then actually getting curves on your computer without then introducing some kind of discretization. But for that whole time, we're going to be pretending like it's a continuous controller acting on a continuous system. The Laplace stuff assumes that on a very deep level, but even when we do simulation, even when we do a step response and we've calculated it numerically, we'll be pretending, or we'll be claiming that that is an approximate solution to continuous differential equations. It gets harder to do the simulation because eventually when we simulate discrete controllers acting on analog systems and we don't have the TC lab connected, in other words, we're trying to simulate the action of a discrete controller on a continuous controller, we'll end up with quite a messy set of code because we'll have a for loop which is doing the small step integration for the continuous system. And we'll have another for loop inside of it, which is doing the big step integration for the discrete system. So just hang on when you look at the code. Also, if you're reading ahead at the code in the repository, there's a lot going on there. I hope this makes it clear. I wanted to have this talk now because for part 1, I ask you to simulate the action of an analog controller on your analog TC lab. And a lot of people get this wrong because they end up simulating the effect of a discrete PID controller from section 7.6 on the TC lab. And that is wrong, right? So for part 1, you are going to find a continuous realization of the real or the realizable PID controller. You are not going to use the position or the velocity form because those are discrete controllers. So just to be very, very clear, the realizable PID has this transfer function. And you will remember that you are able to obtain a state space realization of any transfer function and then use that to give you the differential equations for the simulation that you're trying to do. So that's actually what I want you to do for part 1, is to actually simulate a continuous PID controller. And hopefully, as I'm kind of, this is the second year that we've had the TC lab in this program. And last year, I realized that the TC lab throws this spanner into the works because it places you into, you imagine that thing to be digital when in fact it is continuous, just simply because it's a sampled system. And because we're doing the calculations using that kind of discrete approximation. To do the simulation that I'm looking for, though, and all of the math in chapter 10 assumes that there is no sampling going on at all. So when you look at chapter 10, the one thing you will not see is anything that looks like a delta t or anything that looks like a z. Why? Because we are working with continuous differential equations. And so all of chapter 10 ignores the practical issues that we spoke about earlier today. There's no quantization error, there's no sampling, there's no approximation. Everything is a continuous system. The only problem or the only thing holding us back is that we cannot implement a pure derivative. All of these other things are just assumed to be perfectly well behaved, perfectly analog, right? Okay. So I hope that gives you a little bit of better background of what we're trying to do. I want to end today by reminding you, you'll see that the first part of reading in chapter 10, again, it's kind of just laying some groundwork. We're going to end with closed loop transfer functions, but I want to remind you that you don't have to commit